we don't have to just limit ourselves to the Cartesian product of two sets. We can take a Cartesian product of as many sets as we want. And instead of ordered pairs, the elements of taking the Cartesian product of n sets are called ordered n-tuples. The notation we use is A1 cross A2 cross etc. cross AN is going to be the set of ordered n-tuples A1 through AN such that AI is in capital AI for each I, where I ranges from 1 to n. If all of the sets in our Cartesian product were the same set, then we would just say a to the nth power. Someone recently asked me in office hours if they could write the set of cubes of integers as z cubed, z to the third power. And my answer at the time was, well, no, you can't, because that means something else. And now we're actually talking about what that would mean. If I write z cubed, well, I really say z3, and by that I mean z cross z cross z. In other words, the set of ordered triples A, B, C such that A, B, and C are all in Z. One example, another one aside from this, is example 4.4.5. When we say Rn, we don't say R to the n, we say Rn. Rn is the n-dimensional space. In other words, it's R cross R cross R cross R n times. When we say R2, we're talking about the xy plane, and R3 would be the xyz space. If you've taken Calc 3, you've done a lot of things in R3. For hands-on exercise 4.4.4, notice we have 3 finite sets, and you're taking the Cartesian product of all 3 of those. So you will actually be able to write all the elements of that Cartesian product. So technically speaking, A cross B cross C is not necessarily the same as A cross B cross C. And the reason is the structure of the elements in each set. If you have A cross B, which consists of ordered pairs of the form AB, and then you cross that with C, these elements here are actually going to be ordered pairs. These are going to be ordered pairs where the first element of the ordered pair, the first coordinate of the ordered pair, is itself an ordered pair, and the second coordinate is just an element from the set C. A cross B cross C would be ordered triples. That's not the same structurally as these elements from A cross B cross C. If we were to examine A cross B cross C, we would have elements that look like this. The first coordinate of the ordered pair would be an element of A, and the second coordinate of this ordered pair would itself be an ordered pair consisting of an element from B followed by an element from C in that order. Which tells us that the associative property for multiplication that we take for granted does not apply. It is not true for Cartesian product. Another important fact that will set us up for something bigger later is theorem 4.4.2. Suppose A and B are finite sets, and the cardinality of A is M, and the cardinality of B is N. Remember, cardinality for a set is the number of things in that set for our purposes. And we denote cardinality with absolute value bars around the set. So if the cardinality of A is M and the cardinality of B is N, then the cardinality of A cross B is M times N. Now think about why this is true. Everything in A cross B is an ordered pair of the form A comma B, where A comes from A and B comes from B. There's M choices of A. If you think back to the examples in the first video in the series for this section, there was that systematic way of writing the ordered pairs. We had a certain number of choices for the first element, or the first coordinate of our ordered pair, and we went through all the different choices for the second coordinate. Then we took the next element in the set, and we had n choices for that second element. So we would proceed all the way till we get to m things, each having n choices for the second coordinate. So what that means is we can multiply the number of things in A times the number of things in B and get the total number of ordered pairs. To remind ourselves of what I'm talking about, I'm revisiting the first examples we went through. So A cross B has 2 times 3, which is 6 elements in it. And again, each element is going to be an ordered pair. What was the systematic way for getting all of the elements of A cross B in example 4.4.2? Well, we chose the first element in A, which was 1, and fixing that choice of A, we then chose one at a time the elements of B. So we got these 3 ordered pairs. Next, we went to the next value of A, which was 2, and we put that as our first coordinate in some ordered pairs, choosing elements from B as the second coordinate. So again, we had 3 ordered pairs from that. Because we have 2 elements in A, that gives us a total of 2 times 3, which is 6 elements. This idea is what's called the multiplication principle. We're going to look at it more closely when we study combinatorics, but this is one of the most basic ideas of figuring out how to count things. You can extend this further to say that if you have any finite amount of finite sets, then the cardinality of the Cartesian product of all n of them is going to be equal to the cardinality of each of them all multiplied together. Think about extending this idea when we went through example 4.4.2 again. Corollary 4.4.4 we're not going to talk about because it involves power sets, and we said we're skipping power sets. But there's a fact related to power sets as well. All right. So again, to summarize, the Cartesian product of two sets A and B, which we denote A cross B, consists of ordered pairs of the form A comma B, where little a comes from big A and little b comes from big B. Because it's ordered pairs that we're talking about, A cross B is usually not the same as B cross A. We can extend this idea to n tuples, ordered n tuples, and have an n-fold Cartesian product. And then if A and B are finite sets, the cardinality of A cross B is equal to the cardinality of A times the cardinality of B. I'm not going to ask you to do a lot for this section in terms of exercises. I'm pretty much going to ask you just these 3. I want you to practice this idea to understand the notion of Cartesian products and the cardinalities that can arise when you do various calculations with them.